Okay, so we're going to go over our last little section here, multiple choice. Okay, part 7, multiple choice on the chi-squared and linear regression stuff. We'll kind of remember some things and go over some of those. So here we go. All right, so this first one is just seeing if you know the degrees of freedom rules. So this one, there are 3 rows and 4 columns, and so the degrees of freedom are rows minus 1 times columns minus 1. So I wanted to remind you of the degrees of freedom, all of the degrees of freedom rules. So the degrees of freedom for just a regular mean problem is n minus 1. The degrees of freedom for chi-squared goodness of fit is what? Categories minus 1. Okay, and for a chi-squared test of homogeneity or independence, that's the ones that we put in the matrix. That's the ones, that's the rows minus 1 times your columns minus 1. Okay, and then the other one, the degrees of freedom for a linear regression t-test, that's your test for slope. That's 2 variables. So since that's bivariate and 2 variables, what's the degrees of freedom on that one? N minus 2. Okay, so that's all of the degrees of freedom in a nutshell right there. Okay, so this one on the front page was the rows minus 1 times columns minus 1. So that's why it was answer C. Okay, next, number 2. This is a test for slope. So it's a linear regression test. And it tells us, you know, of course, the null hypothesis is that slope is 0. The alternative is slope is less than 0. So that's interesting. Slope is less than 0 means what kind of slope would it be? We're going to have a negative slope. Okay. Now, we reject the null hypothesis. So what happened? What can you tell me about my interval if I reject beta equals 0? That there is a linear relationship. And it also tells me that there will not, no 0 in the interval. I'm getting 0. So 0 will not be in the interval. Okay, so what I did was I came down here and I calculated all these things. Furthermore, because my alternative is negative, the entire interval should be negative. Okay, so you can come down here and you can calculate those intervals and all that kind of stuff and get your numbers. A and C both fit the bill. Okay, so my thought was, well, how do I tell the difference between those? And I was wondering if it had to do with the 99% confidence and such. Okay, let's do another quick review about how to do a confidence interval. Okay, so in order to do a confidence interval, let's say a confidence interval is your sample slope plus or minus your critical value times the standard deviation of the slope. And what is this part after the plus minus? That is the margin of error. Okay. All right, so this B here, that's the letter B, the lowercase b is your sample slope. Okay, so of this whole interval, what part does the quote-unquote 99% confidence have to do with or affect? Yeah, so your confidence level will affect this margin of error and this critical value. So what I can see is that since these margin of errors are the same on both of those, I'm like, okay, then I don't know where to go with this. There's no way from what they've given me that I can tell those 2 of them. All right, so we're going to go with A or C. Next, number 3. Okay, there it says, here's our hypothesis statement. There is evidence of a linear relationship. If there's evidence of a linear relationship, what are we doing with the null hypothesis? We are rejecting it. And in order to reject the null hypothesis, what has to happen with your p-value at the 10% level? What can you say about your p-value if you reject the null? good. Your p-value is low, so it has to be less than 0.10, and the only one that is that way is A. Okay, next. Number 4. Here is just a straight up interpretation of the way we interpret confidence intervals. So this is confidence interval review. We are 95% confident that the true slope of the regression line is between 1.075 and 1.99. That's a straight up way that we compute this. Which, by the way, review of everything, you could replace this little piece right here with whatever it is that you are estimating. You could say, I am 95% confident that the true, average, that the true proportion, that the true difference between the two proportions, or the difference between the two means, or whatever. Okay, so you could replace that little section for whatever you're estimating. All right, next. Here we use this actually a lot in these problems, where they say if the estimate of the slope is 1.51. Okay, estimate of the slope is that little sample slope, your little b. So your little b is 1.51, and it tells you the t-test statistic is 7.07, so that's your t-score. And remember we talked about how, if you want to find, it says find the standard error estimate S of b. Well, S of b by hand is a pain in the B-O-T, the bot. So you had to do b over t, and you just filled in the numbers, and that's how you get your S of b. Okay? Here actually took quite a, kind of was multi-step problem, so let's go through that. They give you 18 points, so that means degrees of freedom is 16, because there is a sample size of 18. So degrees of freedom, because this is a test for slope. Since this is a test for slope and for linearity, degrees of freedom is n minus 2. All right, then they tell you this. So looky here. The estimate for the slope is negative 3.91. That means this. The sample slope is negative 3.91. Okay? And they say, also, with a standard error, that's the same thing as standard deviation of the slope. It's called standard error because it comes from sample of data, not just the whole population, okay, is 0.84. So we got S of B equals 0.84. So if I have B and I have S of B, then I can use this little formula right here and find T. And if I know my T-score, then I can TCDF and get a p-value. So this was a multi-step problem. You had to first get your T-score by using that B over T, S of B equals B over T. The T-score I got was negative 4.65. So that means my sample is way down there, way down low. And so I TCDF'd from negative 99 to negative 6.5, comma, 16 degrees of freedom, and I got a very small p-value. 0.00013 is my p-value. So, multi-step problem. Find your T-score and then TCDF to get the p-value so you can decide if you reject or fail to reject. This would be the last one, the linear regression, chapter 27, linear regression stuff. Yeah, but this is kind of a little more in depth maybe than what some of those. We haven't seen one just like this before. Okay? Which, we can't have every example, and I'm sure tomorrow will be things that aren't like ones we've done before, but. All right, here we go. We got another interval. It's going from 0.179 to 0.234. We got to interpret it. Now, this is interesting. I am 90% confident that the true slope of the relationship is between this and that. Well, guess what? Instead of saying the true slope of the relationship, they interpret the slope. For every 1 increase in the caffeine consumption, the average increase will be between this and that. So instead of saying 90% confident that the true slope is between this and that, they interpret the slope along with it. For every 1 milligram increase in the caffeine consumption, the average increase, okay, of alertness. Okay, next, here we go. This one you actually don't need to look, we don't use that chart on this one because it's just a t-score. So let's take a look. Here we have a slope relationship, and where we have the variables x and y at the 10% level. So there's my alpha. Okay, so my alpha is 0.10. Sample size is 22. Sample size being 22 means my degrees of freedom equals 20. So my degrees of freedom is 20. All right. So the question is, what's a possible t statistic? Okay, so I got my alpha. That's how much is in my tail, and I need to find the t-score. Okay, so I got my t-score here and here. Because, tell me about this 10%. Is this 10% all in one tail, or is it split between two tails? So, there's my t-score. Now, what did I say? Got your 10% split between two tails. How do I know it's split between two tails in this case? Perfect. Because the alternative is not equal to, then I know that this 10% is split between two tails. If that had been a one-tail problem, then the entire 10% would have been in one tail. Okay? So I've got a lower t-score and an upper t-score. So I'm going to find this t-score, and if I inverse t, 1 tail, comma, 20 degrees of freedom, it gives me negative 1.72. So this is negative 1.72, and of course positive 1.72. Okay? So that means your sample, in order to be in the rejection region, in order for your sample to be in the rejection region, it needs to be at 1.72 or above. It needs to be at negative 1.72 or below. Okay? So the one that meets that criteria is D. Yes? Okay. So they told me that the rejection region is 10%. And because of this, I know that the tails, there's two. So that 10% is split between two tails. Yes, alpha is the size of your rejection region. That's another way of thinking of what alpha is. It's the size of your rejection region. Yes. Okay? All right. Okay, moving on. Here's another one where we have the interval, and we're seeing we are going to reject beta equals 0. So no 0 in the interval. No 0 does not contain 0. And what does this alternative tell you that the slope will be? The slope should be positive. So you need to find the interval that will be completely above 0. And that gives you positive slope. So that's going to be A. That's the only interval that's completely contained above 0 for a positive slope. Okie dokie. Number 10. So this one, I just kind of went all over the map with it, trying to figure out how I could get my answer, and I ultimately determined that I don't have enough information to get an answer. So that's what led me to E. I mean, my first instinct was to do all of these intervals to see if 0's in there or whatever. That didn't get me what I wanted. Okay, and then I have a t-score. Okay, so since I have a t-score, then I could do my, the margin of error. I could at least figure out the margin of error. Well, they're all the same anyway, so that's not going to do me any good. Yes, ma'am. Oh, that's a good question. Is B 0.355, is this a 0.5? Yeah, that's not going to be, because when you subtract that, you're going to get to the negatives. 0.35 minus. See? Yeah, if you, yeah, 0.35 minus 0.5 would be a negative number, so that's a no-go. Okay? All right, so back to this one. So the margin of error is your t-star times your standard deviation of the slope. I there's just too much information missing for me to figure out. I can't even do a T-star because I don't have the sample size. So anyway, I just tried multiple different ways. It's E because they don't give you enough information to do this problem. So yeah, just several things missing there. Okay, hey, this is a good problem because this is going to help. We're going to review the computer printout. So let's review this computer printout. Recall that this line, of course, right here, that's your sample slope that you get. This next to it is the standard deviation of the slope, so that's your S of B. See, that's your sample slope, and this is your standard deviation of the slope. This is the t-score where your sample was located, if the null is true. Here's your t-score where your sample was located if the slope is 0. And this is a p-value to be able to test if the slope is 0. This p-value is used for testing if the slope is 0. Okay. By the way, what's this plain S over here? Do you recall that? Yes, that's the standard deviation of the residuals. So the average amount that the actual y's vary from the predicted y's. So that's the standard deviation of residuals. Whereas this was the standard deviation of the slope. And remember, if you sample many times. So that's all of y'all sampling many times. Y'all all get different slopes from me, and they'd vary about that much on average. Okay, so from this, we want to know the confidence interval. Well, look at all my answer choices. They all give this correct sample slope, so that's not helpful. The thing that is different amongst all of these answer choices is the part behind the plus minus. And the part behind the plus minus is the what? Margin of error. So I know that my margin of error is the critical value times the standard deviation of the slope. This t-star is not the same thing as that t. This t-star is based on what? This is based on confidence. Okay, good. So this is based on confidence and sample size. So for a 95% confident, I'm doing inverse t of 0.025, comma, 8 degrees of freedom. So this number is 2.306. And then I can see here that the standard deviation of the slope is 0.2605. So if I multiply those two things together, it gives me 0.007, which is that 0.601. So that's why that's the answer. Yes. The z-star? Because this is a test for slope. This is a test for slope of the regression line, and that's a linear regression t-test. Test for slope is a linear regression t-test. Okay? All right. Moving on. Okay, this one, one is the only one that's true. The data doesn't have to be in a table. You can figure it out some other way. But the expected counts have to be greater than or equal to 5. That's your large enough for chi-squareds. Expected counts are greater than or equal to 5. Okay, next. Number 13. Okay, this one, all of these answers also are just found straight up from the computer printout. It says that the null hypothesis would be rejected at the 5% level. Well, what tells me if I'm rejecting or not? P-value. So I go look at this p-value right there. And yes, 0.019 is less than 0.05, so I do reject at the 0.05 level. Okay, the second one, the slope is 3.345. And here is the slope right there, 3.345. So the slope of that regression data is 3.45. This standard error of the slope is the same thing as, that's your S of B. That's your standard deviation of the slope. That is 1.316, not what they have written there. Okay, next. Okay, here's another one. You know what? We did this one, something very similar to this on a test earlier in the year where this flipped everybody out. Okay, not everybody, but a lot of people. So guys, if you have got this presented to you, 2.715 plus or minus 0.981, you can create the interval, and the interval is not 0.981 to 2.75. The interval, you need to go the 2.715 plus 0.981 to get this number, and 2.715 minus 0.981 to get this number. Okay. But anyway, based on this, the margin of error is 0.981, and the margin of error is your T star times your S of B. So you know the margin of error value is 0.981. You know T star is inverse T of 0.025 comma 23 degrees of freedom. And so if you have both of these numbers, then you can solve for S of B. Okay, and that ends up being 0.474. All right. Next, number 15. Okay, so here's another one where S of B equals B over T was what you needed. Because they give you T, they give you S of B. So since they give you 2 out of these 3 things, you can solve for the sample slope. Solve for the sample slope. And so I do that. I plug in the values and I get that the sample slope is 3.024. Then I know my answer. It's got to be that one right there because that's the one with that slope, 3.024. All right, number 16. This one's just definition. Expected counts are what you would hypothetically expect to happen if the null is true. Okay, and here is another that the expected counts have to be greater than or equal to 5. That's just straight definition stuff. Okay, moving on, number 18. Okay, so what should you notice about this interval? 0 is in it, so the slope could be negative. This is not the right answer, by the way. I figured out last period that I knew there was something weird about that. So based on this interval, could the slope be negative? Yeah, it could be negative. So there could be, so this question is, which one of these isn't possible to happen? So this could be true. Could the slope be positive based on this interval? Yeah, it could be positive. Now, based on that interval, since 0 is in it, could there be no linear relationship? Could the slope be 0? Yeah, yes. So it could also be that. Could the true slope of the regression line be 2.11? It could be. How about could you reject the null hypothesis? Could you reject beta equals 0? What would you do with this interval? 0's in there, so you're not going to, so 0 could happen. So you know what you would do? You would fail to reject. Since you fail to reject, this one is a no-go. You would not reject it. You should fail to reject it. All right. Here's another one where they give you T is, find the T. They give you S of B. What's this little 0.09 right here? What's this? Yep, that's the sample slope right there. That's the B. So you have B, you have S of B, you can find T. Okay. All right, moving on, number 20. Chi-squareds are all positive, so you need to go all to the right. So E is not possible. All the chi-squared numbers, it's a skewed right distribution. All the chi-squared values are positive. Okay, next. This is a wrong answer also. So this compares the grade distribution of 3 professors. So we have a variable that is the professors, 1, 2, or 3 professors. And we have a variable that is the grade distribution. A, B, C, D, E, or F, A, B, C, D, F. Okay, and then the professors, could be Mac, Miser, or Grable. Okay, so we got two variables. If we have two variables, it's a chi-squared test of independence. Two variables, chi-squared test of independence. Okay, all right. Next, this one you actually do have to do in the chart, and I'm going to teach you how to do that or re-show you how to do it. We did it once, maybe twice, way back when. The reason that you have to use the chart is because there is no inverse chi-squared in the calculator. Okay, so that's what makes us having to use the chart. So the question says we want to have a 0.01 level of significance. Okay, so that's the p-value basically. We want to see where that's located. Okay, so we have a sample size of 100, but that's not how you get degrees of freedom. Categories, there's 10 laundry detergents are chosen, so that's 10 categories. So my degrees of freedom is 9, and I want to find the chi-squared that gives me this p-value. So here's what that looks like. On your chi-squared chart, there's your chi-squared chart, and all of these numbers in the middle are chi-squared values. Okay, so all of these things in this area are chi-squareds. So what we want to do is we want to find, so all of these are chi-squared values. And so we want to find the one that has a p-value of a tail of 0.01, alpha of 0.01, tail up there, and 9 degrees of freedom. So I'm just going to follow this around to where those two match, and they match at 21.67. So that's basically saying I got a chi-squared value of 21.67 such that there's 0.01 up here in that tail. Okay. All right. Yes. Okay. So number 23, I actually could do, this one you could do with chi-squared CDF. So you know there are 12 categories, so the degrees of freedom is 11. Degrees of freedom is 11, okay? The chi-squared value is 23.5, and I want the p-value. Okay, so think about what it's saying is you got a chi-squared value out here at 23.5. What is this p-value? So how do we find that p-value? Chi-squared CDF from 23.5 out to forever. I'm going to even use 999 because chi-squared numbers kind of tend to be large. Comma degrees of freedom, which there's 11 degrees of freedom. So if you do that in your calculator, you get 0.015. And so that p-value is between 0.01 and 0.02. Okay, we're so almost done. Hang in there. All right, this last, man, this problem was just all messed up with the information they give you because, look, they said there were 400 birds. I think that was a typo. There's not even 400, there's not even 4,000. If you added these up, there were 3,960 in the sample that they used. So let's go with that. So I've got 3,960, okay? And so these are the actual grade distribution. So this is what was observed. That will go into your list 1. What is observed goes into your list 1. So I put my 220, my 780, 730, and 2230 into list 1. Now let's talk about how you get what is expected. That's the main thing that tricks people up on this. By the way, how do you know this is a good chi-squared goodness of fit? Are you going to go do the macroeconomics one? Okay. How do you know that this is a chi-squared goodness of fit problem? Perfect. These are claimed ratios. So you have the claimed percentages. So since you have the claimed ratios, that is what makes this goodness of fit. All right, so now the next thing is, how do you do those ratios? If you got this 1 to 3 to 3 to 9, how many parts is this? There's 16 parts. So the first section should be 1/16 of the total 3960. And the second ratio is 3/16. The second expected is 3/16 of the total 3960. And so on. So you put all those in, you run a chi-squared goodness of fit test, and you get a p-value of 0.16. So with a p-value of 0.16, you are going to what? You're going to fail to reject. So if you fail to reject, you do not have sufficient evidence to reject the claim. You do not have sufficient evidence to reject the claim. All right, almost done. 25. Chi-squareds have to always have positive values. And then this last one, our linear relationship between two variables, that's bivariate data. You're looking for the linear relationship between those two variables. That is part E. Okay, very good. Now, there's about 4 things that I have thought of that I thought, oh man, I probably should have shown them one of those, or I should have shown you one of those. There's 4 little bitty itty things, itty bitty little things that I wanted to just throw at you that come from all different places. And so let's take a look at these last minute questions that I found for you. All right, so first one that I wanted to show you, let's do this bigger here. Okay, let's take a look at this problem over here with the tree diagram. Okay, so it may be hard to see those numbers, but basically we have A is 0.8, and then you branch off into X, Y, and Z probabilities. B is the 0.2, and then you branch off into X, Y, and Z. So the question is this: probability of B given that X has occurred. Okay, now do you remember doing a tree diagram before? It was a long time ago, probably back in November. So let's review that. So if I say given that X has occurred, all of these X probabilities will go on the denominator of my fraction. Okay, so let's do that. Let's do these X probabilities. So where are all of my X probabilities on this picture? A and X plus B and X. So those are the total ways in which you can get X. So what I put down here is the A and X or B and X. Okay, so that's the total possible ways that you get X. Now they want to know, given that X has occurred, what's the probability of getting a B? So what part goes on top? The B part goes on top, and when I say the B part goes on top, it's not just 0.2. It's the B and X. So it's this B and X part goes on top. So probability of B and X given that any X has occurred. Okay, and then you would fill that out. And I don't know what that answer is, but that's how you do those. Okay. All right, another one here. We did this yesterday, so let's review this that we had done yesterday. We've got 2 independent variables. The mean of X is 3.5. The mean of Y, man, that's hard to see, isn't it? The mean of X is 3.5. The standard deviation of X is 0.8. The mean of Y is 2.7, and the standard deviation of Y is 0.65. They want you to combine the means. So what can I do to combine them? I am allowed to just straight up add those 2 numbers together. Okay, but combine the standard deviations. Pythagorean theorem. So I cannot just add these 2 together. I have to go the square root of 0.8 squared plus 0.65 squared. And that'll be your answer. Furthermore, suppose that I had wanted the standard deviation of x minus y. What is that? Same thing, because your variability is always increasing even if you're subtracting. Okay. All right. And two more things. The other thing is, what if I asked you, are A and B independent? And you have like a table of values. You know, you have probabilities of them. Okay. So what do we know about independent? Independent, independent, independent. When the fact thing does not change the rate. Good. The fact that you are one thing does not change the rate. So here is the way you would prove that or prove it not to be independent. You would say, you would give a conditional probability. So say like A given B. And you would figure out what that number is. Because you're saying basically the fact that B is happening, what is the probability of A? Okay, if these are independent, then the fact that B is happening should do what with the probability of A? Should not change the probability of A. The fact that B is happening is not changing the probability of A. So if that's the case, when you calculate those two probabilities, what should happen between them? If they are the same, if these are the same numbers, then that means A and B are independent. Because the fact that B happened did not change the probability of A. Okay, is that too astronomical, or are you kind of like, oh yeah, I kind of remember that, and I can plug in some numbers and go with it? All right, and the final thing that I remembered, I might ought to mention something to you about, is we know that on our formula chart, binomial expected is when they say, hey, out of 50 items, how many do you expect to be blue? Out of 50 balls that are in the bag, how many of them do you expect to be red or whatever? Okay? So that's NP. That is on the formula chart. The thing that is not on the formula chart, if they ask you something like this. How many shirts do you expect to pick out of the bag to get a blue shirt? Okay? And what I would have told you is something like, there is 10% blue shirts in the bag, 50% red shirts in the bag, and 40% green shirts in the bag. So how many shirts do you expect to pick until you get a blue one? That is called geometric expected, because see, it's the go until you get a blue shirt. So geometric expected, anybody remember what that is? It's not on the formula chart, but we did discuss it. 1 over P. So let's do that. How many shirts are you going to have to pick out to get a blue one? You will have to go 1 over 0.10, which is 10 shirts. How many shirts are you going to have to pick out to get a red one? 1 out of 0.5, which actually is 2 shirts. So you're only going to have to pick 2 shirts on average to get a red one. And green, let's see, how many shirts do you think you'll have to pick on average to get the first green one? 1 over 0.4 is 2.5. How can you pick 2.5 shirts? This is an average. On average, you expect to have to pick about 2.5 shirts to get that. Okay, that's it. So, my recommendation to you, if you want to do any studying, is to just, at the beginning of each section, there's the different rules. So you might glance back over all the little different rules and maybe flip through some of the multiple choices you had questions on in your 175-page packet that you have. Oh, I will put the entire packet answer key online also. So if you go to Plan Book, in fact, I'll probably do that right now. The entire answer key packet will be online on today's Plan Book page.